Today's topic is regression, and regression is a very important topic in statistics because it's one of the basic models we use to describe a y and x relationship. So here's the topics we'll be covering today. We'll go right up to statistical and practical significance. So why are we doing this? Well, as we stated a moment ago, that we are going to model an x and y relationship right here. So the key thing to know is that we have one explanatory variable, an x variable, and one y variable, which will be the variable of interest that we want to understand. We're going to use a mathematical equation to do this, and you'll be seeing it here shortly. So remember, we're going to write an equation, which is going to be called a model, to do a regression. And the reason we call it simple linear regression is we only have one x and linear because we're using a line. And there's other ways of doing this, but we'll focus on that in later chapters. So the equation right here has two parts to it. One part of it is going to be focusing in on the y part, which we will call predictive analytics, because we're predicting y. The other part of it is going to focus in on the x's, and we're going to call that descriptive analytics. So predictive analytics, focus in on the predictions, the y part of the equation. Descriptive analytics help us describe what's going on, and we have the x's, which do the explaining, or you could say the describing, but that doesn't sound as good. So remember, when do we use this? Well, we use simple linear regression when we have a quantitative y and a quantitative x. There are other things that can be done like logistic or multinomial logistic or multiple regression, but for right now, we're talking about simple, meaning one x, and then we have linear, meaning two quantitative variables where we will fit a line, and regression, which is going to be the equation. So here's some of the examples where we can do it. Let's look at the first one real quick. We have how much do we expect a movie to ultimately make after its opening weekend of 35 million. So 35 million, or the opening weekend, would be the x. We're going to see if the opening weekend explains how much a movie will ultimately make, which is the y variable of interest. So we have to know, when do we apply simple linear regression? Simple linear regression is applied when we have a linear relationship and we also want there to be about equal spread of points, and we don't want there to be extreme outliers. So it's kind of like Pearson correlation. Pearson correlation has those same conditions, and you can look, this second one right here might be a bad idea. There seems to be a bend in the data. There might even be an outlier or a symptom of the heteroscedasticity, the plot thickening. This one's not so bad. There's 1 point right there, so we can't really tell what's really going on. So first and third might be a good application of the simple linear regression, but the second one might have problems, so maybe we shouldn't use simple linear regression for the second one. So here is the regression equation itself, and we're going to write it a few different ways today and talk about the algebra version of it. But it's important to note right here that we have the mean of y given some x. The mean of y given some x looks the following way. What we have is these all points right here have the same x. So now the line should be going through the mean of the points. Even more, the points themselves would actually make a normal distribution around the mean. So it even goes back to the concepts we've learned in other chapters about mean and standard deviation and what is kind of expected. But for right now, realize that the line itself is the mean of the y for a given x. And that's why you see right here, the mean of y given some x. Next, you have the true intercept, which is beta 0. And then you have beta 1, which is the true slope, and then the name of the x variable. Beta 0 would be the true intercept for all points when x is equal to 0, so it's right about there. And then the slope is, mathematically speaking, the rise over run for the 1 unit increase in x. Now later on we will be interpreting that, so stay tuned for the exact interpretations. The next slide has some really great notation for you to know. We'll briefly review it, and then let's look at some R output. You'll notice right here we talked about the mean of y given some x. And then let's think about if we were to take a variable right here where we had a y variable equal to height and an x variable equal to weight. So let's think about the context. I'm going to make up some numbers here, but we're just going to come up with some context for some of these values. Notice we have y bar. which is the average y for individuals in the data set. And this is a sample data set we've collected. So we might say something like the average height of the individuals we've collected is 70 inches. That would be the average of the y variable. Next, we have y, which is the observation. That would be one person in the data set. So maybe someone is 71 inches, and that would be their height. That's one individual, or like one dot on a plot, and it's y observation along the along the y where it would go across. Next, we have right here y hat, which is the prediction, which actually comes from the line itself. So if you were to look at a line right here, the y hat would come from the line, and the dot itself would be where it would hit the y axis if we were to trace across to it. So the dots are the y's, and the line itself is going to be the predictions right there. Standard deviation of the y is variation within the y variable from the mean of the y. The x bar is the mean of the x's. So if you have weight, it'd be the average weight of individuals in your data set. Standard deviation of the x is going to be variation within the x variable. And beta 0 is going to be the true intercept, and beta 1 is the true slope if we had a census. B0 and B1 are usually what we work with because we have sample data, we don't have a census. Let's go look at some R output and see what this looks like and how we will find these values. Let's talk about how to do regression using the reg class package. So first, let's load library reg class to load it up. Then let's load in some survey data right here. Survey data 10 is inside of the reg class package. Now we need to make the model. So we're storing into M, which is just an object. We're creating this thing right here. We're storing into it. What are we storing? A linear model. That's what LM stands for. Next, we have y tilde x, and the tilde is next to the escape or underneath the escape on the far side of your keyboard. So the x variable is going to be weight, and the y variable is going to be height. So we are explaining height using weight to explain it. So the variable of interest is height. The data frame right here is survey 10, and that is where the vectors are located inside of, and you can see them right there. So make sure to name your data frame the name of it, and you can see survey 10 right there. So once we've made this model right here, we're going to go ahead and visualize the model right here. Now if you notice, we get a full visualization very quickly. Don't worry about the confidence and prediction intervals yet, we'll cover them in a later chapter. But we might have some issues with this regression. Well, I see some outliers down here. The line is not going through the center of the points over here, so maybe it doesn't have a good enough linear relationship. There's an outlier over here, and I don't really know if there's equal spread issues. It seems more to me that maybe there's linearity issues or outlier issues, but now we need to go, and even if we might have a little bit of problems, let's go and look at the summary and interpret the summary next. We are going to do a full interpretation of the summary here. The summary starts out by showing you what was called. You made a linear model with a y variable and an x variable, and here's your data frame. So remember, this is your y, this is your x, this is the name of your data frame. Next, you see the residuals, which is how much we miss by. So a residual is going to be the actual minus predicted, so it's a distance your point is away from the line, and this is the most negative residual. This is the most positive residual, so we have the min and the max. The median is the 50th percentile of residuals, and then we have the 25th and the 75th percentile of residuals. And generally, you want these to be about symmetric. You want those to show symmetry. You don't want this here. You notice the min is a lot further away, so that's a further outlier. And then you want the median to be close to 0 because you don't want there to be some kind of bias to your residuals in the positive or negative direction. So now we get to the most important part for this lecture, the coefficients. So when we talk about the coefficients, we mainly want to talk about B0 and B1. So over here, you'll notice this is the estimate of the intercept, which is B0. This is the estimate of the slope coefficient, which is B1. What we can do with this is we can now write the regression equation. Let's write the general format right here of y hat, the predicted value of y, equals B0 plus B1x. And with this, we can now replace the values. Well, y hat is predicted height. So we're just taking the name of the y variable up top. Predicted height, put a little more g on the g. And then B0 is just the coefficient or the estimate of the intercept. So now 56, we'll round it to one decimal, 56.3. And then b1 is the coefficient of the slope. And over here, we put the name of the x variable. Very important to see what goes where for this equation, and we just replace those values. And if you notice, we just have the name of the x variable here, name of the x variables there, and the name of the y variables there. And then we just plug them into the equation and write out the regression equation, which is the equation of the line itself. So that line you saw on the previous screen is mathematically computed via this equation. The last few things in this output are the standard error. The standard error is a metric of uncertainty in an estimate. So if your parents were to tell you, we'll be here at 5 p.m. today, but we could be off by about a minute. Now that doesn't mean they'll be like 1 minute early, 1 minute late, they can't be 2 minutes late, but with that little uncertainty, you wouldn't expect them to be an hour late. So we're saying about the same thing here. I think the estimate of the intercept is about this value, but I could be off by about this much. You want your uncertainty to be small because the uncertainty leads to the t ratio. So if you round these numbers, you'll see 56 over about 59 right there, or 0.59. And what that would be as a ratio is going to be about 95 or 96. So the t ratio there is the estimate over the standard error. So the t ratio is a ratio of those two values. Now the t ratio leads to the p-value because the more extreme on the positive or negative side the t ratio, the smaller the p-value. Because we'll actually in the background draw a t-curve and then plot where we landed. So that's where we landed there at 96 or so. And we'd plot it way off the curve over here. And then we'd do one just as extreme over here. And the p-value would be found that way. So a more extreme in the positive or negative sense t-value leads to a smaller p-value. And the same thing goes for weight, where our uncertainty in the estimate of the coefficient of weight is about 0.0036. The t ratio is a ratio of the estimate over the uncertainty, which is a ratio of about 20. And that's a very, very large t ratio shown by the statistical significance of a very small value of 0.0000000002 or so. That's moving the decimal back 16 times. The last thing right here is the statistical significance codes, which tells you that the p-value is somewhere between these two values. And as long as you have one star, it is statistically significant. Next, we have here the residual standard error, which is how much the model typically misses by. So when we predict height, we are typically off by about 3.554 inches. It doesn't mean we will miss by that or we always miss by that. It just is, we're usually off by about this much when we predict height. And it's also in units of the y. Remember I said we're typically off by about 3.554 inches. We don't really use the degrees of freedom. They're used for calculation purposes in the background of R to create things like the p-values. The multiple r squared, it says multiple. It's just telling you sometimes for the multiple world, but that is your r squared right there. So you can actually get correlation by square rooting that and then checking the direction. Make sure to square root your correlation, then check the direction to see if it goes up or down, because r squared is always positive. It's the percent of variation in y explained by the variation in x, as in 36.13% of the variation in height is explained by the variation in weight, or knowing somebody's weight would get you about 36.13% of the way to understanding their height. Next, we have the adjusted r squared, which will be more important in the multiple world. It's a fair way to compare models that have more variables than others, and also it's going to penalize us for those extra variables. More about that when we get to multiple regression. The F statistic is going to be used as a ratio of what we observe being explained over what we would have expected via random chance. We don't use it so much here. We're going to focus more on the r squared for the practical significance of this model. Then the degrees of freedom for the F are calculation purposes that we're not really going to use. And last but not least, we have the p-value of the overall model, which in this instance, the p-value of the overall model is the same as the p-value. And we'll highlight just that. This p-value right here, which is the significance of the overall model, is the significance of the x variable. And the reason for this is because the x variable points to the xy relationship. So here you notice the intercept is not 0, and here you notice the slope is not 0. So what we care about is a non-zero slope. A non-zero slope points to there being an xy relationship, but a non-zero intercept would not. We have to remember though when making these models that all models are wrong, some are useful. So we're always going to get it wrong. Think about a clock in your house that is 12 hours off. So if this clock were to say 10 p.m., then another clock says 10 a.m., I think both those clocks would have about the same amount of usefulness. But what if one of them said 1 p.m.? Well, the clock that's 3 hours off, you might have to think, wait, how off is that clock? So the clock with being 12 hours off is probably the most off a clock can be, but it's still extremely useful. And that's how we look at our models. All models are wrong. They're always going to be wrong. We'll never get the right model, and even if we did, we wouldn't know it. But some of these models will be useful. And this was said by George Box. Really great quote right there. Really comes to play on how we think about our models. So we are trying to create this regression equation right here, and we're trying to figure out the true quantities of the values. But it's not a physical law. Regression is not a cause and effect relationship like we would have with E equals mc squared right here. We can't say one thing causes another. Same thing idea with correlation. Correlation is not causation. And what we have right here is just an idea of a relationship that we see between the variables. And we'll go into interpreting this in just a little bit. So the truth right here is that we just have estimates. These estimates of the true quantities right here are going to be B0 and B1. So we just see an association and we make a mathematical equation, and sometimes it's too complex for just one variable. That's where multiple regression comes into play. We might have a better way of explaining it in later chapters. So when we do this right here, remember we're just taking guesses or estimates, approximations or hunches on what the model might be. And if you've got different people, they'd have different views on this. Different collections of data will come to different views. And if you collected 3 different sets of data, you'd have 3 different views. We will look at this, especially in 474, and see how we have different variation among different data sets. We oftentimes want to minimize that, and that goes to good sampling and also our sample size and lots of things that can happen within our data set, and we'll investigate that more in analytics. So we go back to the idea of descriptive and predictive modeling. Remember, descriptive modeling is going to focus more in on the right side of the equation, B0 plus B1x. The descriptive side is over here on the right. The predictive side is easier because it's just the y-hat side, the predicted part of the model. So that's just, how does the model predict? Does it predict good? What percent of variation did we explain? But the descriptive side is often harder for people because you're going to need to describe the coefficients themselves. And so you'll need to look at these right here. You'll need to look at the x's and what x's go into the model. So every bit of that, what are the x's that go into the model? What are their coefficients? And describing them and interpreting them is going to be what's most important in descriptive modeling. But when you do predictive modeling, it's merely what are the predictions and how good are they, which is a little easier to do. So let's go look at the regression equation. In the regression equation right here, we have 3 key parts. Right now with simple linear regression, we have the predicted side, and then we have over here the intercept plus the B1, which is going to be the coefficient of the first x. And we oftentimes don't put the 1 on it just because it's the first x and it's the only x in simple linear regression. So once again, these are the truth right here, but we only have the estimates when we do our model. So we often don't note it or notate it with the truth right there. And so what are these values? Well, the intercept is just where it hits the y-intercept. So it'd be right here, B0. And then the slope is the rise over run. But be careful. We're going to have very exact interpretations for these, and we're going to do it for our examples and see some in the notes. So when we do this, remember that the intercept is going to be the expected value when we have a y equals 0 for the observations at that point. And if you look right here, we need to make sure we're only doing this for linear relationships. This one right here, good. But this last one, not a linear relationship. So remember, regression only is applied for linear relationships because we're going to use that line and the coefficients to describe this relationship. So the intercept right here is going to be the average value among all individuals who have an x equal to 0, or the expected or the predicted. Now be careful right here, because sometimes the intercept isn't meaningful. You'll see that in a lot of our examples. So It's rarely important. We're not super interested in it. It's kind of an arbitrary point. When x is equal to 0, we expect the individuals among this group right here to have y values equal to this on average. We'll do some interpretations in a moment, but the slope is going to be what's more important. So going over here to the slope, we have a very exact interpretation. Two individuals. What do we mean by this? Well, think about this. We have a line right here, and then maybe we have people here at 1, people here at 2. Now we've got some data points. Now if you look, two individuals are expected to differ by this amount when they differ by 1 unit of x. That is the expected difference. Like, hey, these people right here also have that difference. These people right here also have that difference. But a key thing to point out is that difference is not always there. We wouldn't always see this difference among all individuals, as in sometimes you have differences that are not that. It's the expected differences. Two individuals or entities that differ by 1 unit of x are expected to differ by blank units of y, where the individual with the higher x in this instance is expected to have a higher y. And we have to use these words like expected right here because this is not what will happen, it's what's expected. Let's look first at our version that we made and then do the version in the note. The slope is going to be this. So remember, our graphic kind of looked, it was decently linear. Kind of looked something like this, a little bit of linearity to it. And there's the line. So two individuals that differ in their weight by 1 pound are expected to differ in their height by 0.07 inches. Two individuals that differ in their weight by 1 pound are expected to differ in their height by 0.07 inches, where the individual who is heavier is expected to be taller. Makes sense, right? Like I have two friends who differ in their weight by 1 pound. Well, I'd expect them to differ in their height by 0.07 inches, where the individual who weighs more is expected to be taller. Another thing we can do with this is we can multiply this by 100. And if we multiply it by 100, think about what we get now. Two individuals who differ in their weight by 100 pounds are expected to differ in their height by 7 inches, where the individual who weighs more is expected to be taller. So you can just multiply by 100 and do a 100 unit difference among individuals or entities. Now remember, this is where you need to practice and try writing this down. I encourage you to write it out on your computer with what I just said. Try rewinding, writing it down, and if you do that, you'll be better for the test because we often have you write this out and you'll hear some of the bad interpretations coming up that I don't really want to say yet. So with this, we have the intercept right here, and the intercept would be among individuals with a weight of 0. Doesn't really make sense. Among individuals with a weight of 0, we would expect their height to be 56.3 inches on average, and that would add, this is not a meaningful interpretation because it doesn't make sense. Individuals can't have a weight of 0. That's how I would write it out, trying to explain to someone. A lot of times people don't ask you to explain the intercept. They're more interested in what is the XY relationship, because that's the significance of the model itself. If the coefficient of the slope is 0, then the model is not statistically significant because it's a flat line. So we care more about B1 than we do about B0. We're going to look at a few more interpretations in the notes right here, and remember, you will need to know how to write these out for the test. Do not write things like for each 1 unit increase in x, we expect y, or y will change by this. Will, cause, prove are all bad words in this class. This is where people lose a ton of points on the test. Do not write this out. So here we go into writing our good interpretations right here. And let's try the first one. Here we're looking at a data set predicting the salary of individuals at a company, and it's the monthly salary. We're using education as the x variable. So when you look at this right here, two individuals who differ in their education by 1 year are expected to differ in their monthly salary by $85, where the individuals with more education are expected to have a higher salary. Try writing it out, try saying it. The more you do it, the easier it becomes, and you just get the interpretation down with practice. To the next one, we'll do one where it is not individuals. Two bills at a restaurant, because this is the context of the example. Two bills at a restaurant that differ by $1. It's always a 1 unit if we do the basic interpretation. Two bills at a restaurant that differ by $1 are expected to differ in their tip percentage. You could say negative 0.23, that will come into play later, by 0.23, where the bill that in their tip percentage, where the bill that is higher is expected to have a lower tip percentage. And that's key right there, that we would need to mention at the end here that the bigger bill is expected to have a smaller tip percentage. Next, we'll deal with census blocks. And here we have census blocks. When they go out and take a census, they have the percent of households that are renting, and they have the response rate from individuals on the census. So two census blocks, that's what we're collecting on, two census blocks that differ in the percent of household renting by 1% are expected to differ in the response rate to the census by negative 0.25, where the census blocks where there's more people renting are expected to have a lower response rate. Try to practice this. This is key right here. You can see the intercept. It's not so important. You might say, well, this one is intelligible, where we'd say something like a census block or census blocks that have a renting percent of 0 are expected to have a response rate of 87 on average. So that would be the expected response rate of census blocks that have no households renting. Try writing these out, try practicing them. Remember, a lot of people usually have problems in this class with interpreting the slope right there. Very, very important interpretation. Last, let's talk about the least squares criteria. When it comes to the least squares criteria, you might be wondering what are squares and what are least squares? Let's get into that. Well, the first thing to know is we call our line the line of best fit, because our line is going to best fit the data. It's going to reduce the sums of squared errors. Well, what are sums of squared errors? Well, here's errors. The error, or residual, and that's the notation for it, is the actual minus the predicted. And remember, we saw this earlier. Remember, Brian's actual value of height is his y, where his predicted, which would be from the line, so this is y hat right here, anything on the line, and then this is a y value right there. But what we're going to do is we have these errors right here. And if we were to sum the errors and find out how much error there is, the sum of the errors would be equal to 0, because some of them are positive, some of them are negative, and the line goes through the middle of them. But how about if we square the errors? So think about what we have here. We squared the errors, and now we have a sum of squared errors. A sum of squared errors. And that's what we're talking about. The least squares means the line makes the least squares. It makes those squares as small as possible. So when we talk about the least squares, we're saying those squares have been minimized so that the line creates the smallest amount of squares, which is also minimizing the error. So we have here the error, which is the actual minus predicted. We are squaring it. That's the second S right there, the sum of the squared error. And then we are summing it, which is the summation right there. So the sum of the squared error and the errors themselves are the residuals. So this is very, very important to what we'll be doing, because this is what makes the line itself. And with this, we can use the equation right here to find out quantities like the slope and the intercept. So the slope right here is going to be the correlation times the variation in, or the standard deviation of y over the standard deviation of x. And the intercept is going to be the mean of y minus the slope times the mean of x. And that's how we can find those values if we're doing the equation. And that does it for today's part of this lecture. Stay tuned for more. Feel free to email if you have any questions.